Hello everyone, I am Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering. Today I am going to discuss on heat transfer. The overview of today's topic, heat transfer, is basics of heat transfer, modes and mechanisms of heat transfer, general differential equation of heat conduction, and numericals. These are the reference of heat transfer. Heat transfer, a practical approach by Yunus and Sengel. And the second one is fundamentals of engineering, heat and mass transfer by Sachadev. Next one is Hallman by heat transfer. And these are the references of the heat transfer subject. Now, heat energy. What is heat energy? Heat energy can be transferred within the body or from one body to the other body. Now, the study of the techniques and methods adopted to transfer of the heat energy is known as heat transfer. How the heat is transferred, we'll see now. Now, if two bodies are there, the temperature will be transferred from one body to the other body if there is a difference between these two bodies. Difference between the temperatures. Okay. Now, always the heat transfers from higher temperature to lower temperature if two bodies are there in physical contact. This means that there will be no heat transfer between the bodies if there is no temperature difference. So always there should be some temperature difference between two bodies in order to transfer the heat energy from one body to the other body. And always the temperature flows from higher to lower temperature. So what are the modes of heat transfer? The first mode is the heat conduction. The second one is heat convection. And the third one is heat radiation. Heat conduction. The conduction always occurs in a solid body. Solid body, and the transfer of heat does between the molecules. If you suppose heat any object, it starts heating and it will heat the particles inside the body. It will transfer from one portion to other portion. Like that, it will transfer the heat from one portion to other portion, vibrating the molecules from its mean position. Now, if you see this example, now at the tip of the rod is being heated. Slowly it will get heated and it will pass the temperature across the body. And if you see the right side figure, slowly the temperature is getting increased. If you see the temperature, slowly it is getting increased from left to right. So in this way, if we heat any object, the particles inside the body get heated up. Slowly these molecules will change their relative position to the other position. In that way, the heat is transferred in the body. So this is the concept of the conduction. Now, the principle of energy conservation and Fourier's law of heat conduction are applied to derive different forms of differential equations to govern the temperature distribution in a stationary body. Now, this is the heat conduction equation where Q is directly proportional to the area and change of temperature with respect to the direction. So here, if you see here, the Q is directly proportional to the area. A is the area. dt by dx is the change of this temperature in the x direction. dx is the direction. Now, if you remove the proportionality constant, you will get the K here. K is the thermal conductivity of the given material. So here you can see the equation Q by A. Q by A is given by small q. The small q is called heat flux of the given object or a body. That is given by minus K dt by dx. If you see here, why you are getting the negative symbol here? Why? If you see the note here, the minus sign is the consequence of the fact that heat is transferred in the direction from higher to lower temperature. That's why you are getting the negative sign here. Now, if you see the nomenclature, Q is the heat flow in a body per unit area, and A is the surface area of the heat flow. dt is the temperature difference, and dx is the thickness of the body in the direction of flow, whether it is dx x direction, dy y direction, dz z direction. So x, y, z, it varies depending upon the directions what you are considering. K is the constant of proportionality, that is called the thermal conductivity of the given material. So thermal conductivity varies with temperature, varies with material. So in this way, K gets varied. And Q is the heat flux, that is the quantity heat transferred per unit area. So conduction equation is given by Q is equal to minus Ka dt by dx. Now if you consider an small wall, a one-dimensional wall here, if you see here, the thickness, L is the thickness of the considered wall, and T1 is the temperature at one phase and T2 is the temperature at the other phase. Now in order to calculate the heat flow inside the given wall in the direction x, see here you can see clearly x direction, so you are considering along x, so that's why it is dt by dx. Clear? Now for a plain wall of thickness, what you are considering in the previous slide, L with the temperatures T0 and TL at the two phases. Now integrating the equation, what you're getting in the conduction. So I write this equation as Qx is equal to minus Ka dt by dx. I convert this, rewrite this equation as Qx dx is equal to minus Ka dt. Okay, now I integrate this equation with the limits. Since x dx is changing along x direction from 0 to L, it is changing from 0 to L, and similarly the temperature dt is also varying from T0 to TL. As we have seen here, the two temperatures T0 and TL are the temperatures at two phases. So I integrate the equation so that I can get, this is my equation, what I'll get, Qx integral of 0 to L dx, 0 to L, the x is changing with 0 to L, is equal to minus Ka integral of T0 and TL with dt. So T0 and TL are the change in temperatures in the considered wall. So ultimately after integrating and applying the limits, you will get the equation as Qx is Ka by L into T0 minus TL. Now if you consider a problem in this, a stainless steel plate 2 cm thick is maintained at a temperature of 50 degrees centigrade at one phase and 50 degrees on the other phase. The thermal conductivity of stainless steel is 300 degrees centigrade, is given as 19.1 watt per meter Kelvin. Compute the heat transferred through the material per unit area. You have to find out the heat transfer to the material per unit area. So you have the equation as Q is equal to Ka by L T0 minus TL. So in this equation, you'll substitute the values as K is given as 19.1 watt per meter Kelvin. L is given as 0.02. 2 centimeters is given, converted into meters. And T0 and TL, initial and final temperatures, are given as 550 and 50. Now if you substitute all the values numerical in this equation, you'll get heat flux. So heat flux is given by Qx by capital A. So small qx is called the heat flux. So in the problem they are asking to find out what is the heat transferred through the material per unit area. So per unit area is given by small qx, that is 477.5 kilowatt per meter square. Now the second mode of heat transfer is the convection. Convection generally occurs in the liquids. So here what happens, the energy transfer across the system boundary due to temperature difference by the combined mechanism of molecular interaction and bulk transport. So as we have discussed, convection needs fluids. So this is how the convection process happens. If you boil water in a vessel, what happens here, because of the density, higher density, the water heated at the bottom will rise up, and the whatever the water, warm water is going up, slowly the heated water goes up and warm water comes down. Okay, in this way the water gets heated up. So the molecules will transfer from bottom to higher level. So there is a change in the position of the molecules, that is called the convection process. You can clearly see in the picture, hot liquid is rising up and whatever the cold liquid at the upper portion is coming down. So in this way the water gets cooled. So this is the process of convection, and the law is given by Newton's, and it is called as Newton's law of cooling, and the equation for this is given as Q is equal to HA delta T. Here H is called the heat transfer rate, and A is the area of the given subject, and delta T is the change in temperature. Again here small q is called the heat flux, and it is given by H delta T. And here delta T is nothing but the change in the surface temperature and the free surface temperatures. Whatever the surface temperature you have and whatever the free temperature you have, that is the difference between these two, is called the delta T in the convection. And convection, you have two different types. One is free and natural, and the second one is forced convection. So in the free natural, it is induced by buoyancy forces, and in the forced convection, it is induced by external means. So by external means, you are forcefully cooling the system by using an external fan or blower. That is called a forced convection system. Similarly, free, you have to free the system with natural air. That is called the natural convection. And same in this also, you can see the problem to find out the heat transfer rate. Okay, so the flat plate. So a flat plate of length 1 meter and width 0.5 meter is placed in air stream at 30 degrees centigrade, blowing parallel to it. The convective heat transfer coefficient is given as 30 watt per meter Kelvin, and you have to calculate the heat transfer if the plate is maintained at a temperature of 300 degrees centigrade using the equation of convection. Q is equal to HA delta T. You have to substitute the values here. H is given as the heat transfer coefficient is 30 watt per meter square Kelvin, and area is given as length and width is given to you. Substitute these values. Ts, so what is the surface temperature given here? It is maintained at a 300 degrees centigrade, and the free surface temperature is given as T infinity is 30. If you substitute all this numerical, you will get the total heat transfer rate in the plate as 4.05 kilowatt. Next mode is the radiation. Radiation heat transfer involves the transfer of heat through electromagnetic radiation that arises due to the temperature in the body. So radiation does not need any matter. The radiation equation is given by a Stephen Boltzmann constant, and that is given by Q is equal to sigma A T power 4. So it is the value of the fourth power of its temperature. So the Stephen Boltzmann constant sigma is given by 5.6697 into 10 power minus 8. So this is the example of radiation, how the sun is being reflected on the earth with the help of the radiation only. So there is no medium required to give the radiation between the sun and the earth. Now if you see the problems in the radiator, so radiator in a domestic heating system operates at a surface temperature of 55 degrees centigrade. Determine the rate at which it emits the heat per unit area. Again they are asking heat per unit area, that is nothing but the heat flux. So that is Q by A you have to find. So the general equation of the radiation is given by Q is equal to sigma A T power 4. Okay, so the constant, both Stephen Boltzmann constant, as we know, 5.6697 into 10 power minus 8 into the temperature, fourth time of its temperature. Temperature is given as 55 degrees centigrade. So it convert into kelvins. Since the Stephen Boltzmann constant is in kelvins, convert your into kelvins. Then you'll get the heat per unit area of the radiator is 0.6 kilowatt per meter square. Now this is the combined example of the three modes: the convection, conduction and radiation. If you see a simple example of boiling a water in a vessel with the help of a flame. Now if you see clearly, the convection is the transfer of heat of fluid or liquid gases caused by molecular motion. Here clearly in the vessel you can see the moleculars are moving its position, relative position, from one portion to other portion it is moving. This process is called the convection. Whatever the molecules getting heated up, they'll slowly rise and move to the top surface. Similarly, whatever the cool portion is there, the top surface will flow downwards to get heat. So this concept is called the convection. And conduction is the transfer of heat or electric current from a substance to other substance by direct contact. If you see the example here, the handle is being direct contacted to the vessel. So there is a conduction process going here. There is a physical contact between the vessel and the handle. So this process of heat transfer is called the conduction. And if you see the radiation, radiation is the energy emitted and transmitted in the form of waves. So the waves you are seeing in the bottom, flames are the waves. So this is the example of radiation. This is the combined example of the three modes of heat transfer. Thank you.
like, share, and subscribe. Hit the bell icon for more updates.